In this section of the course, we're going to discuss discrete random variables, probabilities associated with them, and getting an idea of expected value, which is another form of averages and means, as well as standard deviation. So, something I'd like us to recall is that word discrete. We saw way back when at the very beginning of the quarter, just a few weeks ago. So discrete was a type of numerical variable that we had, and the idea was that it was something that was counted. So something that's counted, like number of siblings, 1, 2, 3, or 4. So with these, we don't really see decimals coming through. There could be some odd situations where we do, but I would say the majority of the time we're seeing whole numbers where we're counting from one number to the next without sort of exact measurements coming through. Some new terminology is the idea of random variables. So these are going to be a variable, which we usually represent with the letter capital X. So we let X represent our variable, and random in that it can be a random occurrence that happens. So to have a certain outcome for our variable, it occurs randomly. So we're going to study our random variables in this section, and our variables are going to have a numeric value that occurs randomly, and that outcome of an event has an associated probability with it. Okay, so like I was saying, X, it is a random variable that can represent each of the possible outcomes. And something that's going to occur with this section with discrete random variables is we are going to organize our work into a probability distribution table. So if you are asked for a probability distribution table or a probability distribution or a probability table, all of those mean the same thing here, and it should look something like this. So some key things that are showing up in this table here, we have our outcomes. So this is a cafe, and it's the number of cups of coffee sold in a day. And we're going to assume that this cafe only ever has these outcomes, no other ones. So this means they either sell 30 cups of coffee, 36 cups of coffee, 42, 48, or 60 cups of coffee. So if I was curious about a day where they sold 49 cups of coffee, according to this table, that doesn't happen. So that would be our random variable. That would be X, would be these numerical outcomes that come from these random events, essentially. Then associated with our random variable is a probability. I'm going to write that as P of X. So we're going to have a probability associated with each of these with the 0.05, 0.2, 0.25, 0.15, 0.35. So reading this table, if I look at that 30 and 0.05 that go together, that means the probability the cafe sold 30 cups in a day is 5% chance. And then if I jump to, let's say, the 48 and 0.15, the probability they sold 48 cups in a day was 15%. So this table tells me the possible outcomes along with the probability associated with that outcome. Then this table should cover all possible events. And what that means is that if you add up those probabilities, it should equal 1. Exactly 1. Okay. One little caveat to that of exactly 1 is if we had to do some calculation to get those probabilities and maybe a little rounding was involved, maybe we'd come out to like 0.9999 or 1.0001. That's totally fine. You should be really, really close to 1 for these tables. But if I added up this table and say I got 1.25 out, that would concern me. That would tell me I have too much information or those probabilities are too high for the table. So to check if it truly is a probability distribution table, add up those probabilities and make sure it equals 1. Also, our rule for probability holds that each of the probabilities should be between 0 and 1. So we can only have positive numbers, and we can only have numbers stuck between 0 and 1. Okay, so as we go through these examples here, I'm going to also walk us through the notation that we're going to be using, because when we write these up, we'll do this mixture of write the probability notation, any calculations we need to do, and then a nice sentence answer at the end. Okay, so what is the probability the cafe sold 36 cups of coffee? So what my notation would look like for this, we're looking for P of X equals 36. So this is where I want to find the probability of the random variable equaling 36. And this is just a matter of reading the table that is exactly equal to that associated probability of 0.2. So there is a 20% chance the cafe sold 36 cups of coffee. Then for the case of or, so we want to find the probability that X is equal to 36 or 48. And our rule holds that if we see or, should be thinking addition. We want to add those two probabilities together. So I want to take the probability of X equals 36 plus the probability of X equals 48. And those two numbers I can grab from the table. So I'm going to have a 0.2 plus 0.15 to get a 0.35. So there is a 35% chance the cafe sold 36 or 48 cups of coffee in a day. All right. What is the probability the cafe sold at least 48 cups of coffee? So at least, that is setting a minimum value. So that means that I want to look at what's the probability we sold 48 or more cups of coffee. So 48 would be the absolute least, and then we would include anything above. So my notation, I would go the probability that X is more than or equal to 48. And what I would do is add up the probabilities that fit that region that I kind of shaded up there on the table. So we have the 0.15 coming from 48 plus the 0.35 coming from 60 cups of coffee. And that would be a 0.5. So there is a 50% chance the cafe sold at least 48 cups of coffee. So notice that with this notation, it would have been the same as if they asked, what is the probability the cafe sold 48 or more cups of coffee in a day? We would use the same notation. The calculation would be exactly the same. So just keep in mind that when you see at least, that is the same as more than or equal to. Okay, next up, what is the probability the cafe sold at most 36 cups of coffee? So now in this case, they're setting a largest value for us. So at most 36 means that'll be the largest, and we can include anything below. So this would be P of X less than or equal to 36. And with that, we add up the probabilities that we shaded up above for a 0.25. So there is a 25% chance the cafe sold at most 36 cups of coffee. So if you see at most, that's going to be the equivalent of less than or equal to. I'm going to add one more in here, even though it's not on the list. But what if I wanted to find what is the probability the cafe sold more than, let's say, 42 cups of coffee. All right, so if we want to find what's the probability they sold more than 42 cups of coffee. So more than or equal to, that would include 42, 48, and 60. But because it's just more than, we would not include 42. So my notation here, what it would look like is P of X more than 42. But notice that this is the same exact calculation that we did for part C there. So this is actually going to be the same thing as finding P of X more than or equal to 48. So it'll be the same process and we'll get 0.5 out. But just with that phrasing of more than, less than, where it's not equal to, then what we would need to do is just use that more than, less than, and you basically just don't include the number that they're telling you about because we're not equal to that value. So that's how we can read the probability distribution table and what it will look like as we work with these discrete random variables. Sometimes these tables will be provided. Sometimes we'll need to create the table ourselves based on the given information. But from there we can calculate probabilities, and then the next videos will look at expected value and standard deviation.